Okay, I think we're going to go ahead and get started. So if the last folks coming in just want to grab a seat so we can kick this off. Good morning. My name is Tiffany Sargent. I work for Intel Corporation. I'm a principal engineer and I direct our IoT solutions. And I'd like to briefly introduce our panelists today. We're really excited for this panel beyond the discussion that we listed because we're going to be showing a joint architecture between our companies we've been working on. This is one of the first times it's been previewed where we show how edge computations and cloud computations work together. And so we've been working on some projects for a long period of time to actually bring this to life. So beyond us just sharing our colorful commentary, we're also going to be showing this architecture for pretty much the first time in this environment. So we're super excited. So first, let me introduce Seshagiri. He is sitting next to me. He's also from Intel Corporation. He's the senior director responsible for IoT cloud platform providers and also global system integrators. And he's from our business unit called the Internet of Things Group. And then I'd also like to introduce Sri Alaprolu, who's a senior manager and responsible for solution architecture for AWS. So wanted to just give you guys a minute to give a little bit more introduction about yourself.
Yeah, I'm Sesh, and nice to be here. Thank you for the opportunity. Thanks, Tiffany, for the introduction. Just a brief thing about my role. At Intel, I'm a senior director. I'm responsible for the cloud service providers in the channels organization, as well as the global system integrator. So I work with the channel part, this cloud providers, as well as the GSIs. Any opportunity that comes through the channel goes through like business qualification, technical qualification through my group. Thanks.
And thank you again. My name is Sri Alaprolu. I lead our solutions architecture practice at AWS. And before I get into that, on behalf of AWS, welcome again. You're actually attending one of the largest public cloud gathering for public sector customers. So excited to be here. Welcome. And over the next 2 days, you'll have an opportunity to sit through 70 plus sessions. Don't worry, you will miss a lot of those because you won't have time to go through all of them. All of those will be recorded and posted online. So use this opportunity to learn as much as you can, peer with your network with your peers, and then have some fun with after our activities and so on. So at AWS, I actually play a dual role. The first one is like I said, I'm a senior manager for solutions architecture. And what that means is my team and I work with customers and help them understand what cloud is, what AWS is, and all of our services, help them architect and optimize solutions on top of AWS. So a lot of architecture, design, whiteboarding sessions, and so on, with the goal that customers are able to leverage our services to the best way possible. That role also allows me to do a little bit of what we call a trusted advisor. So act on behalf of the customer, take the feedback back into our service teams and our engineering teams and help them define roadmaps moving forward. In case you didn't know, over 80% or more than 80% of our roadmap actually gets defined based on customer input. So we act in that conduit. The second role that I perform is I'm actually leading our IoT practice for public sector, so on a global level. Once again, what that means is working with customers, understanding what their goals are with IoT. In some cases, it's fairly well defined. In other cases, it's a very abstract, visionary type statements. So taking that from that point and actually defining as to what it is that they're going to do and defining an architecture to help them actually go ahead and implement. So once again, very excited to be here and share the stage with Intel. Very excited.
Okay, so thanks for the great introduction. So let's talk about why we're here. So our type of panel that we're talking about today is officially titled How IoT Edge Computing Complements Cloud-Based Analytics. So let's talk about what that means and also talk about the format of our panel. So why are we here? Why do we have folks that are really focused on edge compute and really focused on cloud compute? Well, there seems like there's some myths that it's an either or. And then there's also confusion around specifically when do you use edge compute, when do you use cloud compute, how do they work together, what are some of the types of scenarios and use cases that best benefit edge-only compute, cloud-only compute, or a concert of distributed compute. And so as many of you are here focusing on big data and cloud compute, I think this conference would be amiss not to talk about some of the emerging edge opportunities, edge analytics, not only focusing on what we're now calling the edge is the gateway piece, but we're also talking about compute at the earliest point of data ingestion, which is where sensors or actuators or data is actually coming in. What can you do right at the edge to actually start computing, basically doing something to the data to translate it into information at the first point of your exposure to the data? And so over the past several years, Intel has been focusing on technologies to actually make dumb sensors smart through a variety of architectural processes and platforms. And we've been working with various federal customers to seek to understand what are their pain points, how can we help them realize this, but never forgetting that the lion's share of the compute is going to be done in the cloud. And so I've been working as a solution architect with various agencies, various SIs to seek to understand A, what are their problem statements, and B, how we can design architectures to actually leverage some of those opportunities. So in order to facilitate the conversation, I'll be asking these guys up here 5 questions, and then we're going to try and save about 15 minutes for the audience to ask some more pointed questions to talk about edge, cloud, compute, basic use cases for those, and basic opportunities to leverage compute at the earliest point of data ingestion, and then do some really nice data fusion in the cloud. So I'm going to start with some questions, and as part of this, we'll be actually putting up an architecture at a very high level to show you how this works, so you can kind of envision it not only from listening to us, but also visually. So first question to our panelists. So each question is going to be answered by both folks. So the first question is, what types of compute or analytics use cases should be considered for compute at the edge and or the cloud, and why? Have you seen any use cases where one type of analytics is critical to solve business problems versus another? So Sesh, why don't you kick it off for us?
I think before we answer the question, it's good to get grounded on what is edge analytics, right, and what is cloud analytics. Typically, if you look at compute elements that do localized data processing, right, like for example the transformation, filtering, aggregation, caching or local storage, and transmission obviously to the cloud, as well as some screening type of scenarios. Where would you use this type of capabilities? Typically in scenarios where network bandwidth is very low and expensive. So in those scenarios, you don't want to transmit everything that you get from the sensors or back onto the cloud. So examples, some practical examples. Let's take some video processing, right? You are having a camera and it's getting some video feed, and you have a satellite connection, right? So not compatible at all. So you want to put more compute at the edge and only transmit just the relevant data, maybe after filtering, aggregation, transformation, everything. Maybe you're looking for an event, right? Some fire, right? So you want to process and detect locally and then report that event back to the cloud. So those are some of the typical scenarios. For the cloud, it's more like cloud analytics is more when you're looking at multiple data sets, maybe remote sites, thousands of them, and then each of them is getting like sensor data. You want to look at an aggregate picture, right? Maybe you're mashing that up with some data that's coming from the enterprise or from, let's say, some weather data and things like that. So in those scenarios, I think cloud analytics is a natural fit. Obviously, cloud has a much more resources in terms of compute and storage and things like that. you also have to look at the use case, and we'll kind of discuss this more when we add like some practical use cases where these are prevalent. So if you look at the architecture right from the edge to the cloud, every stage that you go adds latency, right? Both in terms of network transmission back and forth as well as processing. So you have to be mindful, look at the use case, define it properly, and then see what makes sense. So, and as I said, like we'll go through more use cases and address those separately. Yeah.
Okay. So, I mean, I'll add on top of that, when we're talking about edge analytics and edge devices and contrasting that with cloud, I want to make sure that it's not either or. It's actually very, very complementary. In most cases, when we're talking to customers, cloud is the ultimate destination. That's where they're going to store the data. That's where they're going to do big data analytics and lots of additional processing. So that's where data will eventually come. And depending on the situation and depending on the actual solution, there will be some edge devices. Now, what do these edge devices do? One, it could be a simple aggregator of sensors that are just feeding data into the edge, and then that device is the one that's communicating with the cloud. So that's one function that edge devices typically do. Second, could be protocol translations, right? So you may have proprietary homegrown protocols that your sensors are talking to. In most cases, those protocols are not understood. You can't use those to talk to a standards-based cloud-based service. So once again, an edge device will allow you to translate that. Third, as you get more into looking at transformation of data, or like Sesh was saying, filtering data, where you may not want to send all of the data up to the cloud, because in some cases it may not make sense to send all of the data up to the cloud. And I can actually give you some examples down the road here, but looking at the way edge devices are used and function and what their function is in an actual solution from start to the finish, they're quite complementary to what the cloud offers. They're not necessarily exclusive to each other. In some areas where we see edge devices doing a little bit more, some scenarios, as Sesh already mentioned, bandwidth connectivity. So think of you have your solution deployed in remote locations where the pipe to connect to the internet may be very small, right? And therefore, you don't want to constantly communicate and transmit data back and forth to the cloud. Instead, you may want to use your local processing using edge devices, do some level of aggregation, and then figure out when and how what you transmit to the cloud. The second scenario would be connectivity itself is quite intermittent. So think of, for example, in the public sector space, think of a ship that has processing and sensors on board that is at sea. You will have satellite-based connections and connectivity will be there, but you don't want to take up all of that bandwidth for your sensor-based communication, right? So you may want to do some local processing and then only transmit the really valuable data back up to the cloud. And then hopefully once you dock, you're able to sync all of that and take advantage of that. Another scenario could be filtering data where, once again, don't send everything. If you have a scenario where you may want to look at key aggregated data points and triggers and only send data when that trigger is met. So lots of use cases where edge can absolutely complement what cloud does, so it's not a either-or condition.
So one of the reasons that you might want to also consider this concept of distributed compute, and that's what it's sometimes called when you're pairing edge compute with cloud compute, is cost. So if you look at some of the use cases that I've had some experience with, the cost to send data that, let's say, doesn't change. Let's say a sensor every minute is sending across, maybe it could be any type of communications, especially ones you have to pay for, like let's say across 3G or satellite. You're paying a fee like every time you send like 5 degrees, 5 degrees, 5 degrees. By enabling, let's say, a dumb sensor to become smart, by implementing some of the technology at the edge, you may then, and it's pretty common sense, but from a cost perspective, it can amount to a significant amount of money. Only send data that's been filtered or aggregated or computed or even fused in some more complex edge environments to the next point of the system as needed or as required to actually drive to decision making. And I think this cost factor is a way to also look at why you might want to invest in understanding distributed compute, because in some of these cases, once again, I've seen come to light, the cost savings can be pretty significant as you're looking at some of the comms aspect of that. So I think these are some important points as you might be sitting there listening to, wow, this technology seems really exciting. How can I implement it, and then how can I pay for it? So these are some of the pieces when you do a really strong end-to-end solution architecture design. These are some of the points that you can start looking at. What's the value proposition of it?
It's a very important point that you brought out, Tiffany. The cost per compute or cost per storage. Typically, we've had the benefit of enjoying Moore's law, right? So, Intel has been pioneering in that, like cost per compute or cost per storage drops off significantly. Whereas the cost per network transmission, it's not exponential, right? It's kind of linear. So that kind of, with the proliferation of devices and data that is coming through that needs to be processed, you have to keep in mind that at the edge, you can have more compute, more storage. In the cloud, you can have more compute and more storage, but the network doesn't scale that way. So you kind of you're forced to, from an economics perspective, to kind of put more compute and storage as data proliferates. So.
Do you have any other comments, Shri?
No, I agree. It's a delicate balance, making sure that as you start moving compute and analytics onto the edge devices and more gets shifted, the burden also starts increasing on the customer. So it's a balance between how much do I want to do on-premise using my own edge devices versus how much do I want to transmit into the cloud and take advantage of the mass scales of economy that I get in the cloud. So it's a balance. There are absolutely scenarios where doing more on the edge makes sense. In other cases, it actually makes more sense to do more in the cloud. So depending on the situation, we'll have to decide which one and combination ratio makes more sense.
And also too, before we, if you can put up the next slide, sir, for the architecture. But before we have a nice discussion on this, one of the things you also have to start thinking about too, from a cloud perspective, is as you start having these devices out in the wild, I'll say, or do more edge compute out in the wild, you then have to start thinking about a device management cloud system in order to manage the cloud aspects in itself on how to do the distributed compute. So there starts to also emerge another kind of cloud play. So I've actually had put up here, and this is the exciting Intel AWS IoT joint architecture. And I'm going to defer to Shri and Sesh to talk about what are some of the key ingredients, to explain the diagram and talk about the drive of both edge and cloud compute. So Shri, do you want to start the discussion this time?
Okay.
Okay.
So I'll kick this, and Sesh, please feel free to add anything that I may miss. And I'll try to concentrate more on the AWS services side of the house. But this is an example of taking a solution approach end to end, right? As opposed to saying my portion is the cloud and your portion is the edge. This is an approach where we're looking at it comprehensively from all the way from the sensors to edge devices, and then how are those edge devices going to communicate with the cloud, and how does the cloud functionality help in solving the business problem that the customer is attempting to solve. And then at the bottom there on the slide is one of the problems that customers face as they go beyond pilots and POCs is device management. As I onboard lots of sensors and devices across the globe or across the corporation, it's a huge problem, right? How do I know which devices are secure? How do I know which ones are trusted? All of that. So on the top section, which is AWS IoT architecture, which I'll give a little bit of background on that for those of you that are not familiar with it. Customers have been doing IoT solutions on AWS for quite some time, so it's not new. They have stood up EC2 instances, deployed pub/sub brokers on them, and started communicating with them, and things work. The challenge, however, that most customers, when we're talking to them, say is actually twofold. One, it's a lot of pain to scale as their solution starts scaling. It's a pain to start scaling those environments and managing them themselves. The second is it's taking time away from what their actual focus should be, which is my solution, what actual benefit does it provide to my business or my organization, versus focusing on the underlying infrastructure. So with that in mind, and taking some of the pain points that customers have expressed, we announced AWS IoT back in October at reInvent, our 2015 reInvent, as a fully managed cloud-based service that provides the key ingredients for any organization, small or big, to start doing IoT solutions in the cloud. Some of the key components of the service, it's actually multi-component based. Authorization and authentication, mutual auth, secure communications from day zero, right? So the only way you'll communicate with the service is through a TLS channel. And it's a mutual certificate-based authentication so that we, on the service side, will trust a device when it's connecting to us because we know that certificate has to match. Similarly, once the authentication happens, authorization as to what sorts of things is the device able to do. Extreme fine-grained control, if you're familiar with IAM, Identity and Access Management, allowing customers to define exactly what each one of those devices are able to do in the cloud and will allow the services to do on their behalf. So once again, full control back to the customers. And then message broker, that's where the communication, so once the authorization and authentication happens, your messages from the devices are coming into the message broker. Simple way to think about it is a horizontally scalable pub/sub broker. So as you connect more devices, as devices are pushing more data into the cloud, that broker will seamlessly scale itself horizontally, allowing you to push more and more as you get more devices online, no additional burden on yourself. Pub/sub broker then also has additional components such as rules engine, which is, so as messages are coming in, earlier example, for example, let's say temperature in this room is coming in as a data point. You may want to define a simple business rule that says, if the temperature is above 70 degrees, do something, right? That something could be alert a HVAC administrator or alert the building administrator, or perhaps take that data, insert it into a separate system that will trigger a subsequent workflow, and so on and so forth. So Rules Engine will allow you to do lots of inline processing as messages are coming in at scale. It has a lot more complexity that will be available to you as well, whether you want to do machine learning, predictive machine learning right on the fly, or being able to do visualization of the data as it's coming in. So lots of capability that Rules Engine provides. Shadow is another feature which retains the state, last known state of the device, so that if there is a connectivity problem with the device where the device may go offline, your applications will continue to work off of the shadow. Versus in the past, when that happens on an EC2-based pub/sub broker, generally applications will start failing because the device is not reporting in as being connected. So taking all of that into account and building the capability where customers literally plug their sensors or their edge devices into the cloud, securely connect, communicate, do at scale processing, and then eventually when the data passes all of the service layers or components within the IoT service, you have access to a lot of the platform services, whether it's S3 just for simple storage or Redshift, machine learning, and so on and so forth. So in one way, IoT acts as the front door where your sensor-based data or data that you want to pump in an automated way comes in at scale. And then it's bidirectional communication as well. So in most cases, what we've seen customers doing is sending data into the cloud. But in a lot of other cases as well, data points come in based on some analysis that you're doing near real time. You may want to send instructions back to the devices to do something. So back to that example of 70 degrees, now it's 72. Maybe the instruction back to the device is activate the HVAC, right? So you could do that bidirectional flow as well. So that's what the AWS IoT platform is all about, and I'll let you focus on the...
Yeah, the architecture is very complementary. If you look at the Intel parts in this joint architecture, it's more on the edge and security and device management, as you pointed out. On the edge, you have multiple compute elements, right? Like the sensor modules or the gateway, which does the aggregation and filtering, or it could be intelligent wearables, right? Where they're running some specific analytics, right? Those kind of things. And the good thing is part of compliant to the AWS architecture, you have a device SDK that runs on these devices that allows you secure connectivity to the cloud, right? So very, very important. And the other important aspect is security. So Intel is very, very, strict on security because like every device that you throw in the field is a security exposure, right, potentially. We have something called hardware root of trust, right? So we make sure that the certificates are attested and inserted and validated with our device and security management, and then appropriately insert the certificates into the AWS IoT cloud. So very key aspects. So we are leveraging some of the technologies from Intel Security, which used to be McAfee before. Now it is under Intel Security brand. So the other aspect is like, we look at the overall architecture as a control plane and data plane, right? So the control plane is where all the provisioning, certificate management, and all that happens. And then the data plane is the sensor data actually gets collected and sent over to the cloud. So very flexible. And then you can see right on top of the AWS IoT platform, it enables a rich set of applications and SDKs and APIs. So third parties can develop applications both on the cloud and because of the SDK environment provided at the edge on Intel gateways and device SDK from AWS. Those third-party applications can run on the edge as well. So let's say you have a scenario where you need to do you've developed some applications on the cloud, and for some reason you think that because it's a near real-time requirement or something, some of those analytic applications, you can kind of drop it on the edge as well to run. It's the same architecture, same instruction set, so it kind of makes sure that you have a flexible architecture should the need arise.
So I think if we want to, up-level the architecture, I think you can think of it solving four main principles. So the first one is connectivity. There's a connectivity plan across. There's a manageability plan where this works to manage in concert. You've got security is a third. And why is security important? Because we have an end-to-end security solution opportunity where we know as you're putting in place different aspects of the solution that we know that the end-to-end plan is secure. So on top of the connectivity, manageability, and security, you also have an interoperability aspect. And that's really important. It's not only system interoperability, but it's data interoperability. So I think as you think about, extrapolating this diagram, into some simple principles that are actually pretty challenging to solve that I think you guys did a great job doing. I think, if you walk away feeling that those challenges have a solution, that's something that you can feel confident about if you look to apply some of this as a reference architecture. So I want to just kind of share that piece. So I'm going to ask now for a few use cases to share before we go up and have some audience questions. So Sesh, why don't you start with sharing a couple of use cases, and then Shri, and then we'll open it up for questions. So those of you who have some questions, just start thinking about those, and then we'll call on you after the use cases.
Sure, thanks, Tiffany. So a couple of use cases. So I think you might have heard of, earlier during this summit, Intel has worked with Michael J. Fox Foundation, right? So this is basically monitoring and diagnosis of Parkinson's disease. So basically, the patient actually has certain sensors and devices, right? It's very simple. Like you have a smartwatch that has a accelerometer, right? And an Android phone. So that's basically your edge compute over there, right? And but what is important is the wearables here are analytics enabled. So there are algorithms that run on those devices, the smartwatch and application on the Android phone, where you are able to detect balance, gait, activity level, and certain activity recognition, and sometimes even sleep patterns, right? And if you mash it up with certain data like heart rate sensor and the pulse and things like that, you can run a rich set of analytics. And most of it you can run on the edge for pattern detection, right? In this case, we've run about almost like 1 gig of data per day per patient. It's a lot of data, right? So instead of sending all the raw data, often you may not have the bandwidth, especially if you are in public places or going out and things like that. So a lot of that can be done on the smart device itself, right? And you may be interested in a certain event, like for example, a fall, right? Or some tremors, right? Usually associated with Parkinson's disease. So those kind of scenarios, it may be good to run those analytics on the device itself before transmitting to the cloud. So that's one example. The other example I would say is let's take a look at law enforcement, right? So let's say you have some cameras in street lights and stadiums, and it's public places where large events are happening. Law enforcement may be interested in some criminal suspects and things like that, right? So, and you're taking video feeds. You may also be interested in other events such as where are the parking spaces, right? So you want to do a better and more intelligent.
That would have been helpful today.
Yeah. Better and intelligent, traffic congestion management. So what is of interest here is maybe there's a suspect that police is interested in. So you may download a profile of that suspect on the camera itself, and you can do image processing and pattern recognition, face recognition on the edge itself, and immediately alert, right? The local police and law enforcement. So those are some of the scenarios. Otherwise, it would take a lot of time collecting the video feed, transmitting over a congested network into the cloud, and then doing the processing and then alerting. So those are some of the practical scenarios where edge processing can be used more efficiently.
And I think to add to that, Sesh, one of the things that you were alluding to is that the power of processing at the edge. And if you look up on the diagram, there's something up MCU, the microcontrollers, and also the gateway. Intel's been investing in some silicon, but also, and this was previously announced, most importantly, I think there are some new features on some of the silicon and the MCUs, whether they be something that many of you have heard about, which is Curie, or else silicon that can actually be more used in an industrial space. Is those of you who are looking in the depths of the silicon, there's some pattern matching capabilities, and we also have an opportunity to actually expose those through neural network processing and analytics. So we've been, as a company, looking at how to dig deeper into the edge to help really manage some of the extensive amount of data that's being collected. Because one thing that you often hear is that today there's a lot of people data collection, but as it goes to machine data collection in the future, it's going to grow at new levels. So I think these are some of the important points about not sending all the data, especially if it's repeat data, up to the cloud. And I think this is a great segue. And so, Shri, you want to talk about some of your use cases?
So a couple of examples, and actually I'll go with three. The first two I'll touch on will be more of where edge analytics and processing at the edge actually helps put a more cost-effective and better solution for the customer. And then the last one will be more of where all data is streamed up to the cloud, it's near real time, and it's actually being used. So let's say you have a criminal justice or law enforcement situation where body cams, police cameras, all of those you're probably reading in the news. So think of a scenario where a camera on the uniform is typically not activated all the time, because if it is, then it's capturing a lot of data that's probably not as useful, right? So instead, if you have sensors on the uniform that are picking up voice, decibel level, and let's say there is a trigger, so all of that data based on the voice gets sent to the edge unit, maybe in the cruiser that's sitting in the car. It's being analyzed, and based on certain triggers, it could either automatically activate the camera or alert the officer to activate the camera. So for example, if the officer walks up to a struggle or a large crowd and there seems to be an issue, right? You can use the audio or voice commands to be able to trigger whether the camera should activate itself or not. Now, once the camera activates, maybe you want to store that data temporarily or perhaps stream all the way to the cloud. So depending on the situation, you can decide either or. So in that scenario, you're not always streaming data to the cloud. You're using your edge device to trigger and decide and do some processing to figure out when data should be transmitted up to the cloud. Another example could be you have a large water distribution pipeline. You probably have, I mean, a lot of the utility companies already do this. They have sensors that are monitoring water pressure in the pipe to make sure that there is no leak along the way and so on, right? And those sensors are capturing data points every few milliseconds. So think of, instead of sending all of the data up to the cloud, because hopefully for the most part of the time, that data is consistent. There is no pressure drop, right? So use the edge device to figure out and filter and decide if it is valuable enough to send up to the cloud. So when there is a water pressure drop or change in water pressure and the value changes, you're now able to communicate up to the cloud and actually start streaming. Perhaps from that point on, for the next, let's say 10 minutes or so, you want to send every single data point, because maybe you want very granular change of data that you want to capture and store in the cloud as well. On the flip side, an example of where data is constantly being beamed up to the cloud and being used is Street Bump. I don't know how many of you have heard of that. It's an application, or actually a solution, that's deployed in the city of Boston. What Street Bump does is, as you're driving on the streets of Boston, and let's say your car or vehicle that you're going in hits a bump or a ditch, right? You're probably going to jerk up and down or move up and down. So what city and the local startup community has decided is taking data that's GIS or graphical information about the road maps and so on, which is open data, putting it in the cloud, taking data from your smartphones, and use that data as the accelerometer in the smartphone moves up and down as you drive over a ditch, transmit the GPS coordinates when that happens, near real time into the cloud, and then now you're marrying the two and saying, where exactly am I noticing those bumps happening consistently, right? You're applying some analytics on top of that. You're able to predict and actually isolate and pinpoint where the city crews, maintenance crews will have to go, right? Instead of driving around and waiting for complaints to come in, you're now able to pinpoint exactly where the problems are. And that's a scenario where all data points, as long as it meets that bump or accelerometer reading, it goes up to the cloud. So multiple ways in which you could do, depending on the situation. You probably want to lean a little bit more on the edge versus more on the cloud.
So with that, I'm going to open it up to questions. Does anyone have a question for our panel? Yes.
So two questions, actually. The first one is, where do you see the standards for the sensors sending the data to the gateway and MCUs and all the way to the cloud going? Do we have the right standards to enable such integration to be seamless? And the second one, how much of the compute is distributed right now on the gateway versus the MCUs? I'm assuming it's based on the Wind River. The Intel technology is based on Wind River technology.
Yeah, so let me take this. On the standards part, we are working very closely with the IIC, right, Industrial Consortium, and then it's now called OCF, I think, right? So it used to be OIC, and then all joined, right? So they've kind of converged to form OCF now. So basically, all the protocols, all the data formats, everything. I mean, the software that runs on the gateway is able to kind of interwork with the sensor modules, right? So some of the technologies that you will see, right, like Zigbee, Z-Wave, 802.15.4, right, 6LoWPAN. These are some of the communication interfaces, and pretty much like the data formats are kind of make sure that they are industry standard compliant, so it ensures a lot of interoperability.
Can I add something to that too? I think one of the biggest challenges you have in this space is you've got what they call brownfield sites, where you have thousands of sensors already out there. And so how do you enable them to make them smart? You have two paths for that. First is you can try and merge them onto a board with an MCU, and then those boards may have different comms strategies related to them, like, and we're looking at new ones like LoRa and narrowband IoT for that family of MCUs. And then the second piece is, as the gateways need to find and configure thousands of sensors in the brownfield environments. There are actually companies that specialize, and we can drop some of that technology right on the gateway so they can go out and find and help configure some of that. And if you're in Fed, there's actually some Fed certified companies that do that. But some of the biggest challenges of actually not only doing the design, but now you're talking about implementation, is understanding and having the ability to absorb a wide field of brownfield sensors to make them smart. And so as part of your solution strategy, all of us up here are solution architects, we work with different folks to provide recommendations on what your use case is for that. Sesh brought up the fact that we're doing a lot with the standards community. That's true, but in the brownfield, we recognize that that takes a huge challenge. And to your point, your question related to MCUs versus gateways, it depends on the use case, frankly, and that's part of the choice of the designer of the solution. So
yeah. And on the connection to the cloud, we support like MQTT and then WebSocket. I mean, depends on like what the scenario is. Sometimes MQTT is not appropriate. We may have to go WebSocket and so on. So pretty flexible architecture.
And to your point about Wind River, we always like Wind River because it's part of Intel, but we're also compatible with other scenarios as well. So that is part of, once again, the solution plan. Okay, was there another question, sir?
Yes. In the street lamp example, we have 250,000 street lamps in New York City. Each of them could be sensor enabled in many, many ways. Each of them, we know in law enforcement that we need imagery to be retained a minimum of 7 days. There are many scenarios where we could imagine that these would be sensor activated. ShotSpotter, for example, will activate noise sensors and trigger imagery and illumination. Right. But there are important scenarios where there may not be sensors that would trigger the creation of imagery. Robberies in bodegas, knife point robberies where there's no gun. Yet perpetrators will flee. We need to follow them across street lamp to street lamp as they take their hoods down and reveal their faces or get into cars and reveal their license plates. That means we need to run these cameras all the time. How can edge devices assist us in reducing the load on the system that would come from running 250,000 points of imagery all the time in order to capture these random acts of violence that we can't very well predict.
Yeah, let me try to answer that. So you can do multiple things, right? Like, let's say you have a policy, right, where you, for the normal video capture, you may be doing low resolution imaging, right? And then use your algorithms to kind of detect an event and then start capturing the high resolution imaging, right? And nowadays, I think if you equip the cameras and the endpoints with local storage like SSD, or nowadays like memories and storage is becoming a lot cheaper, right? 3D NAND type of technologies where you can store a lot of data locally itself, process it, and then only retain and store the relevant data, right? And to your point, when you are looking at a scale of 250,000 street lamps, it doesn't make sense to transmit every piece of video feed back into the cloud. You may kind of think of it like you're kind of pushing the cloud to the edge, right? That itself is like, I mean, we are getting into something like a fog computing, right? So the 250,000 street lamps with local storage and analytics capability, think of it like a cloud extension, right? You can do some more intelligent algorithms. It all depends on what is the type of event that you are detecting. You have to go through a lot of training of these algorithms and then kind of approach it that way.
When we see 7 people fleeing from a drugstore,
Yeah.
so that something
Yeah,
happened.
something happened, yeah.
Sri, do you want to add into anything
so-
up before we close out the
Yeah,
panel?
so not exactly on that particular use case, but a similar use case where we have partners working on solutions that are smart intersections, more in the smart city space, where traffic routing and optimization of flow of traffic in a city like New York City, for example, is a huge problem, and so is here, right? So think of leveraging sensors along the way in multiple intersections to decide and feed that data into cloud and analyze that data to figure out how long should the signal 3 miles from now stay green in order to optimize the flow, right? As opposed to always doing it based on particular time or particular day of the time or time of the day. So that's another example where it's not as intensive as video feed because these are small bits of pieces of information that's going up and down, but the video feed is retained locally. So that's another example of where data is getting fed in from multiple sources, analyzed, and then instructions go back down to the subsequent intersections to keep the lights on and off, to keep the traffic flowing as smoothly as possible.
So in summary, I know we're out of time, but if people want to come up and ask us from the stage, happy to stay a few minutes to discuss. I saw some additional hands. One thing to kind of summarize, and I think you brought up a good point, is that designing solutions is really hard. There's a lot of different pieces, but one important thing, and I think that's what we also hope to represent on the stage, is that you don't solve it alone. So, Intel and AWS is showing, some of our architectures up here, but when you're talking about complex analytic development or, maybe having a Xeon chip that would normally run a server on a gateway, so it's, able to meet your specific user requirements to do additional storage, right, or so forth, we need to look at a broad ecosystem of analytics partners, people developing niche algorithms, local solution providers. So we all up here recognize we can't win it alone. So it's all about partners to drive forward. So with that, I'm going to close the panel, and let's give our experts a round of applause.
Thank you.
And thank you, everybody.
Thanks, Tiffany.